Hello everyone, welcome to lecture 38 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture we will continue our discussion on negative index metamaterials. Here is the lecture outline. We will have the discussion on debut of optical negative index materials. We will discuss how we can make optical NIM negative index material using paired metal rods, nanorods, and then we will discuss the general recipe for construction. So, let us first discuss the debut of optical negative index materials. Why it is important? Because we need to understand the initial discovery and the importance, right. So, negative refraction was first observed in the microwave range. However, scaling it to the optical range is crucial for both theoretical understanding and different practical applications. Now, there are some challenges in scaling. So, directly scaling down the microwave metamaterials or negative index material structures to create optical version isn't feasible, and this is primarily due to the significant fabrication challenges and fundamental material limitations. And there is also difference in the metal behavior, because the electromagnetic response of metals in optical range is vastly different than that at lower frequencies, where epsilon is extremely large and the metals basically behave like nearly perfect conductors. Now, new approach for optical negative index materials need to be taken. So, that will allow getting unique electromagnetic response of metals at optical frequencies that allows the excitation of the surface plasmon resonance. So, this phenomena could provide a new way to achieve the required negative permittivity and permeability for creating optical negative index materials, and this method is not available at microwave frequencies. Okay. So, if you look from the experimental characterization aspect, so a key challenge in optical negative index material research is basically the difficulty in experimentally verifying their properties, which is way more complex than with the microwave NIMs. Okay. And also there are fabrication limitations, like most reported optical NIMs are fabricated as thin planar layers using techniques like optical and e-beam lithography. Okay. So, this makes it impossible to perform some standard experiments that rely on a bulk NIM structure, right. So, it is not possible to directly observe the negative refraction, right. So, you can think of some wedge like structure. So, here the thinness of the optical NIMs prevents the direct observation of negatively bent light beam. So, that was an experiment which was successfully conducted in microwave NIMs, but not in optical domain. Next is the lateral displacement, that is like if you think similarly, the sub-wavelength thickness of this NIMs sample will make it impossible to observe any lateral shift of the light beam. This was another method used to verify the negative refraction based on geometrical optics. Okay. And then there are some ambiguity in anisotropic materials. Okay. So, methods that rely on measuring the direction of the Poynting vector at inclined interfaces are not reliable for unambiguously determining the sign of the refractive index in anisotropic material. So, there is basically ambiguity in this kind of anisotropic materials. So, another thing is that there are natural negative refraction. That means you can observe negative refraction as an intrinsic property in some uniaxial media, and it has been observed in some natural crystals such as calcite and yttrium orthovanadate, okay, or YVO4. Okay. So, it is important to differentiate these properties with your negative index material, and when you make negative index material, it basically requires that the frequencies at which the material is going to exhibit negative electric response, the same frequency it should also give you negative magnetic response. That means they should overlap. Okay. So, this can be achieved by using artificial materials made of some periodic metallic structures. Okay. So, as was basically done in the case of microwave as well. So, that is how you can achieve negative permittivity, right. So, the electric response of such material like periodic metallic structures can be designed to mimic the Lorentz model, where the key frequency parameters like omega naught and omega p, there is the resonant frequency and the plasma frequency, can be controlled by the design of the lattice and the element itself. So, you can create your own material which has got a custom designed plasma frequency, right, and resonance. So, when you combine the electric and magnetic responses, the main challenge that you see in NIM is basically coming from there. Okay. So, you need to properly combine them. Okay. So, a negative magnetic response, you can say that those have been extensively studied at gigahertz frequencies and higher. Okay. Like the condition for simultaneous negative epsilon and mu from Vasilago's seminal paper is also reported to be sufficient, but not necessary. Now, there is an alternative approach to achieve this negative refractive index in a passive medium, and that could be to design a material where the real and the imaginary parts of the isotropic permittivity, that is, if you write epsilon as epsilon prime plus I epsilon double prime. So, this is the real and the imaginary part, and similarly if you do it for mu, that is written as mu prime and I mu double prime, this is the real, this is the imaginary part, then that has to satisfy this condition, that is epsilon prime mu double prime plus mu prime epsilon double prime will be negative. Now, this would lead to a negative real part of the refractive index. So, your n, which is basically n prime plus I n double prime, given a square root of epsilon and mu, and when you have both epsilon prime and mu prime negative, you basically get that negative index. Okay. So, now let us see how we can obtain optical negative index material using paired metal nanorods. We have seen this kind of structures earlier, so we will go into a little bit more details here. Okay. So, the necessary condition for a negative index material can be achieved in an array of coupled nanorods. So, it was shown in an early paper by Lagerkov and Sarichev, okay, that a pair of metal nanorods can have a large paramagnetic response. And then Podolsky and his group showed that such pair of metal nanorods are also capable of diamagnetic response, and most importantly they can give you negative refractive index in the optical range. So, following this kind of theoretical predictions, the first optical metamaterial with negative index of refraction was experimentally demonstrated by a research group at the Purdue University by using a layer of paired metal rods like this. Okay. So, this is the building block of the metamaterial, which is nothing but a pair of nanorods, as you can see here. Okay. So, an AC electric field parallel to the length of the rod. So, you can see the electric field and the magnetic field direction here, and this is the direction of the wave falling from the top. Okay. So, you can see that an AC electric field which is parallel to both rods basically can induce parallel currents in both rods. Okay. And then you have the magnetic field which is basically oriented perpendicular to the plane of the rods, that can cause anti-parallel currents in the rods. Okay. So, this anti-parallel currents basically cause the magnetic response of the system, right. So, you have this kind of a system, right. So, the magnetic response will be dia or paramagnetic depending on whether the wavelength of the incoming magnetic field is basically shorter or longer than the magnetic resonance of these coupled rods. Now, the two parallel rods, they basically form a open current loop, okay, which basically acts as a transmission line with a current resonance. Now, such a current loop is closed at the ends of the rod pair through the displacement current. Now, for normally incident light, which has got electric field polarized along the length of the rods and the magnetic field perpendicular to the rods, you will see that both the electric and magnetic responses can exhibit resonant behavior at certain frequencies. So, above the resonance frequency, the circular current in this pair of rods and the displacement current that is at the end of the rods can lead to a magnetic field that is basically opposing the external magnetic field of the incident light. So, in this design, the electric component of the incident wave excites a symmetric current mode in each rod pair, whereas the magnetic component basically gives you antisymmetric modes, right. So, the excitation of the plasmon resonance for both the electric and the magnetic light component in an overlapping frequency range will result in a resonant behavior for the refractive index, which can become negative above the frequency as was previously predicted, right. So, this can be thought of as a resonance in an optical LC network. So, this will behave like the inductor and the gaps will behave like capacitors, right. So, the metal rods can give you the inductance L and the dielectric gap between the rods can give you the capacitive element C. So, this kind of structure can be fabricated using e-beam lithography, right. So, this is the designed unit cell of the paired nanorod array. Okay. So, as you can see this one, okay, and this basically shows the field emission scanning electron microscope, that is FESEM image of a portion of the sample, and you can get a closer look here of a pair of nanorods, how they look like. Okay. So, this is a single pair of nanorods and this is the pattern that is made, and this is basically the unit cell that is repeated periodically, and these are the dimensions mentioned here, right. So, how do you get a optical NIM using this paired metal nanorods? So, you need to find out the complex coefficients for transmittance and reflectance that are needed for the retrieval of the refractive index, which can be measured directly in the paired nanorod experiments. So, you can obtain transmission T equals modulus of T square and reflection R is modulus of small r square. This spectra can be collected with spectrophotometer using linearly polarized light, okay. And along with the experimental investigation, the optical properties of the paired nanorods can also be studied from simulation using 3D FDTD or finite difference time domain methods, right. So, this particular figure basically illustrates the result for the phase measurements, including the phase anisotropy and the absolute phase shift, both of which are basically compared with the 3D FDTD simulations, right. So, this is the phase anisotropy delta phi in degrees and this is wavelength, okay, on the x axis. So, the phase anisotropy curve delta phi for the transmitted light, okay, it shows a strong resonant behavior with negative value as much as minus 100 degrees, okay, somewhere here around the communication wavelength of 1.5 micrometer. So, these are the legends, okay. So, you can see this represent phase anisotropy in the transmitted light simulated, and then without the light only the circles are basically the experimental one. Similarly, here you have a square for the reflected light with the line and then only the square for the experimental one and so on, okay. So, these two are for the transmitted and the reflected light, and these are basically the absolute phase shift calculated for parallel polarization and then you have for perpendicular polarization, okay. So, it is a busy graph, so we can go through it in steps and see what you study from here. So, if you look into the inset of the figure, you can see that the phase shift of the sample with respect to an air slab of the same thickness, okay, there is a typo, it should be just minus 61 degrees at so this is for the perpendicular polarization, this is for the parallel polarization. So, perpendicular parallel sign are mentioned here. So, this is done at 1.5 micrometer. So, the magnitude of this value is well below the phase shift in an air slab of 165 nanometer, okay, where you get phi r equals 40 degree at 1.5 micron, so that you have the negative phase acquired in the sample to be around minus 21 degree. Now this negative value basically indicates that you have negative index of refraction, okay, and that is for those particular wavelengths. So your effective index of refraction is basically coming out to be negative. So this is a method to basically measure, okay, along with the simulation, that what is the phase shift of the transmitted light. Now you can see that a high transmission of about 25% is obtained for 1.5 micron. So based on the effective parameter retrieval technique, you can obtain effective index of refraction for both the two polarization for reflection and transmission coefficients, right. So this particular figure shows the zoomed view of the real part of the retrieved index of refraction using the experimental data and the simulation results. So experimental studies of the nanorod sample provides a value of n, which is minus 0.3 plus minus 0.1 at 1.5 micron. Okay, so this is the value. Okay, this is the zoomed version shown here. So this result is basically in good agreement with the simulation and experiment. As you can see, there is a very good overlap here. Okay, so the optical negative index is actually possible, okay, in another kind of structure as well, which is called the inverse of the coupled nanorod structure. So you can think of an inverse structure that is nothing but pair of elliptically shaped voids, means holes that you are making on metallic films. So in this case, a negative refractive index at about 2 micron was basically reported. So 2 micron is typically in the near infrared to mid IR range. I think this is in NIR range anyways, yeah, it's close 1.5 and here you get 2. So this is the structure, okay. So this is the schematic. So you are basically having this kind of voids, okay, and this is the SEM image or scanning electron microscope image of the structure. So what is happening here? So in order to construct the coupled void structure, okay, you need to begin with two thin films of metal which are basically separated by a dielectric spacer, and then electrically shaped voids can be etched into the two metal films that can form paired elliptical voids, okay. So this basically creates the inverse of the original structure, which is basically paired metallic rods or ellipses, okay. So in this both this kind of samples, okay, they should ideally exhibit similar resonance behavior if the orientation of the electric and the magnetic fields are basically interchanged. So here this is the direction of the wave falling, this is the direction of E field and H field. So this is nothing but a result of the Babinet principle, which is useful to note here is that an inverted NIM, inverted negative index material such as elliptical or dielectric or rectangular dielectric voids that you can make in a metallic film are basically physically equivalent to paired metallic rods which are embedded in a dielectric host. So this basically gives us increased flexibility in designing NIM structures that are actually reliable using current fabrication methods. So because this one becomes easier to make. So what are the general recipe for fabrication? So while the two earliest optical negative index materials discussed have proven that negative index materials are indeed possible at optical frequencies, they both however possessed significant losses which are indicated by large imaginary part n double prime that you see in the effective refractive index. Now based on our discussion about the sufficient and the necessary conditions of the negative index of refraction, we can basically categorize the NIMs into two categories. First one is double negative NIMs, in which the Veselago requirement of both a negative real part of permittivity and negative real part of permeability is basically satisfied. You can also have another type which is single negative index material, where the condition, the necessary condition, that is epsilon prime mu double prime plus mu prime epsilon double prime should be negative. So, this one is fulfilled. Okay. However, you just have real part of the permittivity to be negative, but not of the permeability. Permeability real part is positive. So, you can express the figure of merit of negative index materials in terms of the effective permittivity and permeability, and it can be given like this: FOM equals minus modulus mu epsilon prime plus modulus epsilon mu prime divided by modulus mu epsilon double prime plus modulus epsilon mu double prime, right. So, the NIMs that we have seen with pairs of nanorods and nanovoids, they are both belonging to this single negative index material class, okay, and they exhibit a low figure of merit. Although both the negative epsilon prime and mu prime can be realized based on electric and magnetic resonances respectively, it is not a good practice to combine the two types of plasmonic resonances at overlapping frequency range, right. The reason is, first, it is typically very difficult to obtain a system where both resonances will occur at the same frequency, and second thing is that any plasmonic resonance will always bring loss to the system, right. So, since an electronic resonance, it is not necessarily, or you can say it is not really necessary in order to obtain negative epsilon prime, you should basically try avoid using a electric resonance in the design. So, a possible solution to this generic problem would be to just use a resonant magnetic structures along with a non-resonant metallic structure that basically provides a background negative permittivity over a broad spectral range, including the wavelength band where you will see the magnetic resonance happening. So, this is not hard to achieve because noble metals such as gold and silver, they have negative permittivities at optical frequencies below their plasma frequencies, right. So, just by adding a metallic film above and below a magnetic resonator, for example, you can basically get the necessary negative permittivity for a negative index material. So, Zhao and his group, they proposed an alternative method to achieve this background negative permittivity. They proposed by using pairs of continuous metallic wires that do not have electric resonances at that wavelength of interest. Okay. So, then a magnetic resonance with a negative permeability can be obtained by including appropriately designed metallic pairs or plates. So, the general guidelines above result. Okay. So, the general guidelines that you see here basically result in a fishnet kind of a structure that is also known as a double grating structure, and which is today's prevailing structure for negative index materials for optical frequencies. So, you can think of this resonant structure which is having negative mu, and this is basically a non-resonant structure, means a broad over a broad frequency you can get this negative permittivity. When you mix them together, you get this fishnet kind of structure. Now, in the fishnet structure, the pairs of broader metallic strips basically provide the negative permittivity via asymmetric currents, whereas you can see that the pair of narrower metallic strips, that is wires, they act as diluted metal. So, the fishnet can be behaved as a resonant magnetic structure that is combined with a non-resonant electric structure. So, it is important to note that this fishnet structure, okay, the pair of narrower strips basically act as off resonant wires, and at that wavelength where magnetic resonance basically occurs in the broader strips, they simply provide a background negative permittivity. So, based on this popular structure, fishnet structure, several groups around the world has demonstrated negative index of refraction in the near infrared and even the visible ranges. So, here is a SEM image of the fishnet structure that is discussed by Chettiar and his group. Okay. So, this sample was fabricated using standard e-beam lithography, e-beam evaporation and lift off process. So, this schematic of the unit cell of this fishnet structure is shown here along with the incident polarization, okay, in these two figures shown at 540 and 720 nanometer respectively. So, what you see here is that the white one tells you about silver, the bluish one is basically the alumina. So, this is basically the fishnet structure. This is just a cut section to show you which material is which one. Okay. So, the properties of the plasmonic resonance that you see in the structure can be visualized by simulating the field distribution in the sample at few interesting wavelengths. So, here you see the field maps, the color basically tells you about the magnetic field and the arrows shows you the electric displacement, right. So, the retrieved effective parameter for the fishnet sample is shown here. So, figure A clearly indicates that the electric behavior, which is the real part of the permittivity beyond a electric resonance that comes around 540, okay, is similar to that of a dilute metal. So, you can see it is just going negative throughout, okay, and the magnetic resonance as you can see happens around 720 nanometer and it is giving rise to, so this blue one is basically the magnetic one. So, it is giving rise to a negative effective permeability which is needed for, okay, double negative NIMs, right. So, in this particular figure B, you can actually see that the negative index of about -1 can be achieved around this wavelength, which is 725 nanometer, that corresponds to red light. Okay. So, this is as a byproduct at the other polarization of the same sample, it will also display single negative response which can be seen at slightly shorter wavelength of 710 nanometer and all. Okay. So, it is not surprising to notice that the FOM of the single negative, okay, band is only 0.5, which is basically much lower than the double negative one, right. So, that tells the story of how you can make negative index metamaterials at optical frequencies. So, with that we conclude this lecture. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.